Okay, what's up, everybody? Welcome to another fun day of proof set theory and logic. Now that we're done with the syllabus day, we get to get into the real stuff. So I hope everyone has their note packets and everything. Any questions from last time? Any concerns or issues that have arisen since we last met? No? Okay, well, let's get into it. So last time we started talking about propositions. A proposition is a statement that is unambiguously true or false. You don't necessarily have to know which one it is. You just have to know that it has to be one or the other. There were some instances we found of propositions last time, some instances we found of things that weren't propositions that might seem like propositions, and some where it became kind of difficult to tell. Statements involving, for instance, variables, right? It became hard to tell, are we making a statement that is not a proposition because we have to specify what value the variable has, or are we reasoning more generally, for instance, about polynomials, in which case the statement may be a proposition. So this just tells us some stuff that is relatively obvious, which is to know whether or not something is unambiguously true or false, we have to know what we're talking about, right? If I say, it is always raining, and you say, is that unambiguously true or false? Probably the first question most people would ask is like, where, right? There are probably some places where it's always raining. I actually don't know that. Is there a place where it's always raining? Is there?
Um, there's this place in Venezuela that's like two conjoining rivers where it rains about 98%, but it's not constant, it's really close.
Okay, okay. So for the audio for people online, apparently there's a place in Venezuela where it's pretty close, but not always. So I guess that is just universally a false statement, but pretty close to being a true one. So today we're going to talk about kind of the first natural thing you would do after defining an object, right? We've talked about propositions, at least kind of loosely defined what we mean by a proposition, a statement that is unambiguously true or false, though a statement about what. Still need to do a little bit more of these details to make sure that we're actually talking about it in a really formal way. But the next thing you do after you build an object usually is you have, there's two kind of competing ways of looking at this. So here is the idea of it. Anytime you have some things in math, you pretty much always start asking how you can put them together and break them apart. That is, if you've got something, almost always, one of the first things we do is we say, hey, how can I take this thing? How can I break it down into simpler pieces that are perhaps easier to deal with or understand? Similarly, you could say, okay, if I've got some simple pieces, how can I take these things, put them together, and get new, more complicated things? With propositions, this is relatively clear. After all, we all, speak a language. We do this constantly, right? It's not the case that we struggle to, take a couple of sentences and string them together. We're doing it all the time. I'm doing it right now. People do it a lot. So we combine propositions, usually just automatically in English, using conjunctions, ands, ors, quantifiers to some extent, like always or never or for all, for none. People use those last two, I guess, a little bit less casually. We also use single kind of operations, right? Like not, right? Something that would switch the value of something. So the first thing we're going to do is we're going to say, hey, we've got a notion of propositions. How can we put propositions together? How can we break them apart? And if you notice, it's really the same question, right? As soon as you start to talk about how to put two things together, you can immediately ask the question, okay, if I've got something, when could it have been made out of two simpler things? So putting things together and breaking things apart is usually basically the same question in mathematics. It comes down to the same thing. It's defining an operation that takes two things or more than two things and produces one new thing. Could have been produced from two simpler things. So there's always this kind of sense of going up and going down, right? In some sort of a complexity hierarchy. So the easy ones that we start with are very natural. The first one would be conjunction, and, right? conjunction, junction. What's your function, right? So the P and Q with this little wedge, it looks like an A with no line in between. We will see where this notation historically comes from more when we start talking about sets. This is quite similar to the symbol you may have seen for which looks like this, right? And the symbol for the union of two sets looks like that. These are basically a pointy version of each one to kind of make sense of it not necessarily being about sets. So either way, if you could just accept it, and for us, if you have two propositions, one of them P, one of them Q, you can say P and Q, and let this denote a new proposition, which is true when P and Q are both true, and false if either one is false. Information in a convenient, easy to look up way. We could build a truth table. So let's construct a truth table for P and Q. What is a truth table? Who has seen a truth table so far? Everybody has seen a truth table. It's kind of an obvious thing to do. So here's the gist of it. You take your variables, and then you take your P and Q. Actually, let me write these slightly higher up so I don't have to run too low on the board. P, Q, P and Q. You make a table out of it in the very obvious way. That is, you draw lines in between things. And then you go through all the possibilities. So P could be true and Q could be true as well. In that case, P and Q would be true, since P and Q is true only when both of them are true, right? Okay, P could still be true, but Q could be false, in which case P and Q would be false. Yeah, okay, everyone's picking up on this. This is pretty straightforward, right? So the rest of the combinations, P could also be false, in which case Q could still be true or false. And in either situation, you have at least one false. So the answer is false and false. Okay, so we made a truth table. It's not too bad. You can see how you could do this for progressively more complicated propositions you build out of simpler ones using something like a conjunction. We could also use, say, a different connective, a different thing to hook two propositions together and make a new proposition. Let's use a disjunction. So disjunction. The disjunction, which we will denote by this V symbol, this little upside down wedge, yeah? We'll read it as P or Q, P disjunction Q, whichever you prefer. It's just or in the standard way. But there's a little bit of ambiguity with or because the way we use there we go. There's a little bit of ambiguity here. Let me make sure this actually contains everything. Save. Okay. There's a little bit of ambiguity here because the way we use or in standard English does not always correspond to the way we'll use it here. That is, we use or in two different ways that are inferred by context, right? Do you want the soup or the salad? A correct answer is not yes, right? It's one or the other, but not both. However, other times you could say like, oh, how will the weather be later? And you'll be like, I don't know, it'll be snowy or it'll be cold, one of the two, right? You can also, it could be snowy and cold at the same time. So sometimes we have an inclusive or, sometimes we have an exclusive or. I'm imagining most people have encountered the difference between the inclusive and the exclusive or. Here, with disjunction, we will let this represent the the disjunction of P and Q is true if either P or Q is true, or if both of them is true, at least one of them, and it's false only when both are false. So let's make a truth table for the disjunction P or Q. So we'll take P, we'll take Q, we'll do P or Q, bada boom, nothing fancy here. Just make our good old-fashioned table. So you got true, true, false, false, true, false, true, and false. Let's go through each situation and figure out what P or Q is going to be. So if P and Q are both true, is P or Q true?
Yes.
Yes, obviously, absolutely, right on. And if P is true and Q is false, well, hey, at least one of them is true, so it's still true. So you got true, same reasoning for the next one, true. And the only situation where it's false is if both of them are false, right? Okay, cool. So disjunction, not too crazy, right? Ands, ors, basic English, everyone's cool with this. All right, fun. One quick question. If you look at these truth tables, notice we've got two different variables, two propositions, P and Q. And if we're making our truth table, how many rows do we need? Yeah, so there's four. So if you have n propositions, you would need 2 to the n rows. So all possible combinations of n zeros and ones, n true and falses. Yeah. So you can see really quickly that if you're trying to deal with a lot of propositions, truth tables will swell to a unmanageably large scale that may be best dealt with by, say, a computer or something like that. But you can still make them. They're a useful tool. I will have you make a extremely frustrating number of them on your first homework assignment. Because while everyone looks at these and says, okay, this is easy, I can do this, as soon as you start chaining these together even a little bit, that is, it is very easy to make a mistake as soon as you have a highly compound proposition, even just involving ands and ors. It can get messy really quick, right? It might seem really easy to come up with the truth table for P or Q, but if you wanted to make a truth table for P or Q and Q or R and R and Q, oh, not A, and, this is much less obvious what it should look like, right? I've still only got 3 things there. I've only got ands and ors. Maybe you can see it and immediately know what it'll look like, in which case, good for you. But most people probably look at this and go like, I don't know what the truth table should look like. And it is kind of a good skill to have, to be able to see one of those things and know how to just iteratively go through it, break things down, and produce a truth table. So I'll have you do it a bunch. It'll be annoying. You'll probably do your first homework and be like, oh my God, I hope this class is that. No, it won't be. We won't just do truth tables the whole class, but for the first assignment, you will do a lot of them. So, enjoy. Um, anyways, yeah. So what other things can we do? Well, these first two are pretty easy, but the next one I think trips people up a little bit, which is implication. So, oh, I got a little bit of feedback there on the mic. Proximity, perhaps. All right, definition. The proposition, if P is called an implication, and is denoted I'll even make it simpler. P arrow Q is false only when P is true and Q is false. So here's why this one trips everyone up. Be different. That is, this actually looks like. Let's start talking through some examples of it after we do the truth table. I think a lot of people, this is the easiest one to make mistakes on. I'll show you why. So first off, let's make a truth table. So construct a truth table for P implies Q. Okay. So if we do this, we'll put a P column, we'll put a Q column, we'll put a P implies Q column. Chapow. All right. P could be true or false, and correspondingly, Q could be true, or false, respectively. And now we've got all of our P's and Q's exactly the same as the other tables. Okay, cool. implication is false only when P is true and Q is false. So P is true, Q is false. That is the situation where you get false. Every other one is true. I think people don't like this for some reason. I think people want to say, oh, false implies true, that should be false, right? But we're going to say that's true because it may be the case that Q can be true without P being true. What the implication says is that the truth, if P is true, that tells you that Q is true. And so the only case where something does not imply something else is when the first thing is true and the second thing is false. That is, here is a good example. If it is snowing, then it is cold. It could be the case that it is not snowing, but it is still cold, right? That is this situation right here. Not snowing, still cold. But this would be a false statement if it was snowing, right? We know that the statement, if it is snowing, it is cold, is a true implication, broadly speaking, I guess, depending on how you consider things cold. Lots of people like to be tough and say, no, it's not. But, other than that, I would say, okay, fair enough, that makes some sense. But this is one that trips people up a lot. There's not much more to say about it other than, I guess, people get tripped up on it. Think of if it is snowing, then it is cold, and it will help you remember whether or not the only situation where it is false is this one. That is, that if it is snowing, then neither snowing nor cold, for instance, today, right? So still true. It could be not snowing, but still cold. Still true. It could be snowing and it could be cold. Still true. It's snowing, but not cold. Yeah? Okay, cool. Right on. Implication. Fun. So there are a few things related to the implication P implies Q. Let me pop back over to the other board here. Nice. All right. Things related to that get special names. These guys are pretty straightforward. For the implication, P implies Q, the is implies P, the contrapositive, is not Q, P, and the inverse is not P, implies not Q. You might be looking at this and saying, wait a second, what are all of these weird symbols right here? These this looks like a minus sign sort of thing. Not. That is, suppose I should define next, and kind of confusingly is not immediately defined next in your lecture notes. Perhaps an oversight on my part. Definition, negation of P denoted by this symbol, looks like a minus sign with a little bent end, is the proposition that is true when false, and false when P is true. That is, it is the opposite, right? It is read not P. Okay. Okay. We can implications here, these related implications. The converse, contrapositive, and inverse. Okay, let's go in through them. So let's use the example of if it is snowing, then it is converse of that statement.
It's cold, then it's just snowing.
Exactly. If it is cold, then it is snowing. You can tell immediately that the converse is not necessarily the same as the original implication. Is you might agree that if it is snowing, then it is cold, right? You might say that's a true statement. Okay. But if it is cold, is it always snowing? No, there are plenty of days where it's cold and there's no dang snow. So we can switch between these pretty easily, okay? We can say, hey, the converse, just flip the order here. The next two maybe seem a little bit more mysterious, but they're just adding knots. So the Q, then not P. So let's do that with the snowing and cold. So if it is snowing, then it is cold. If it is not cold, then it is not snowing. Huh. Contrapositive, the same as the original. We will talk about this plenty. So it turns out that the contrapositive is logically equivalent to the original statement. What is logical equivalence? That's the next thing we'll talk about. We'll get there in a moment. Sort of. On the other hand, the inverse seems perhaps different. The inverse says not P implies not Q. So if it is snowing, then it is cold. Right? What would the other one be then? If it's not snowing, then it's not cold. Okay. That doesn't seem right, does it? It could be not snowing, but it could still be cold, right? If you look at these, the converse, it's contrapositive, which the contrapositive of the converse is the inverse. Oh, wow, that sounds complicated. But hey, you can see these are all kind of hooked together. So we might use these terms throughout the class to say like, well, that's not true, but the converse is true. Or, that's true and the converse is true. So on, right? Okay. That last situation is a kind of important one. When something is true and its converse is also true. In fact, if P implies Q and Q implies P, it sort of tells you that P and Q are saying the same thing, right? That would be something like saying, if it is snowing, then flakes are falling. And if flakes are falling, then it is snowing, right? Yes.
It's just when I don't think your mic is working.
Oh, God. Oh, man. Okay. Well, hope it's, is it not? Situation if it's not, because then I will, ooh, wow. Maybe the battery is just low. Let me flop that out. How on earth do I open this freaking thing? Joys of technology. All right. Hey, that is good. I hope that we didn't lose audio. I hope we didn't lose audio for a bunch of class right there. That would be unfortunate. I had to re-record the last lecture because we lost audio. So I don't want to re-record this one too. Let's see. Maybe I can just do like some kind of cheesy like dub over my video with some voice. Okay, fair enough. So the contrapositive, the inverse, negation, all the good stuff. Fun. The next thing would be logical equivalence. So this is all about implication and the converse. So definition, two propositions, P and Q, are said to be logically equivalent if they have truth value. We use the connective. It looks like implication and a backwards implication to denote this and pronounce P left and right arrow Q as P if and only if Q. So if and only if, logical equivalence. That's what we say. Okay, fun fact. P if and only if Q is logically equivalent to P implies Q and Q implies P. We'll show that by constructing a truth table, but first let's just make a truth table for P if and only if Q. So example, a truth table for P if and only if Q. Okay, so we got our P's right here, we got our Q's right here, we got P if and only if. Now, one thing that I think people can kind of get into a little bit of a trap on here that they don't fall into with ands and ors for some reason is that this column is telling us whether or not the proposition P if and only if Q the case that by putting this arrow in between the two of them, it automatically makes P and Q assume the same truth values. It could be the case that they have different truth values, and this statement is false, right? So let's go through all the situations. I'm going to have to kind of write this false, false, true, false, true, and false. And when is P if and only if Q true? Exactly, when they have the same truth values. So when they're both true statement, otherwise in the middle cases, it is false. Okay, cool. So P if and only if Q says that P and Q tell you the same stuff. If you know one of them, you know the other one, right? Okay, fine. Over here, and you see this implication. Notice this one is true when both are true. It's true when both are false, but it's false when one is. Let's do implies P in the next column. What goes on when Q implies P? Well, the first and the last column are still both, or last row are still going to be true. These two will just flop. Yeah? So what if you did and?
Oh,
If you took this one and this one, it's only true when both are true. That's in the first row and the last row, and either of these two rows, at least one of them is false. Okay, so let me put this right here. P implies Q, and Q implies P, writing kind of small, I apologize. Things, if you want to parentheses around them, yeah? Well, if you do this, you get true, false, false, true, and wouldn't you know it, look, true, false, false, true, that is the exact same as right over there, yeah? Telling you that they mean the same thing, right? Oh, hey, P implies Q and Q implies P. That is exactly the same as P if and only if Q. Hence the notation. Arrows go from P to Q and one from Q. Seems reasonable. For the people online, let me really quickly shift back over so you can see what I was pointing at. P implies Q, same as Q implies P, and P implies Q. Cool. Actually, wait, can everyone see that over there? Ooh, I need to zoom out a tiny bit. These are the slight variations we have to make in these first days of lecture. Apologies for the annoyance and confusion. Good. Okay. All of the angles are working good, and we have all the board on there. Okay, fun. So, if and only if statements, implications. All right. So, implication and as logical equivalence. Fine. All right. Far through section 1.2. I am happy to see you're getting as far as we are, because the next thing that's up is tautologies and contradictions. So, we'll keep it going. Oh, come on. Sidebar, these are the worst whiteboards I've ever had to deal with. I don't mean to belittle the equipment in Whitmer Hall, but my God, I do use like it is a frustrating situation. So there we are. All right. Let's get on to talking about tautologies and contradictions. So definition. A that is always true, regardless of the truth values of the component proposition it comprises. So that is a tautology. Notice this proposition. That is, it has to be formed from connectives. Let us do an example. And of course, let's make it more fun. P or not P is a tautology. So here's what we'll do. True, or it could be false. Here's not P. That could be, well, if P is true, this is false. And if P is false, then this is true. And then P or not P. Well, it's or, so it is true precisely when at least one of the things is true. Yeah? Is one of the things true in this row? I kind of drew on that T and made it look like an F. Yes, so that's true. Is one of the things true in this row? Yes, it is true. Situations where the corresponding column in the proof table only has T's in it. Can you imagine what a contradiction might be? All false, right? Exactly, exactly. Definition. Contradiction is a proposition that is always false of the truth values of the component or that it comprises. Okay, fair enough. What is an example you could imagine? If we did P or not P as a tautology, what about P and? Yeah, exactly. Not P is a contradiction. Let's show it. So truth table. Okay. P, you got P and not P. Chapow, chapow, chapow. Across, across, down. True, false, false. Is only true if both things are true. Do we ever have two T's in a row? No. So false and false. It is false no matter what the value of P is. Cool. Okay. Contradictions, tautologies, fancy words for always true. Now, but let me just double check and make sure we are running right on time. This goes, all the way up to 11. I thought it only went 10:50. Great. We have time for examples. Let's do it. Going back over, let's do a little, you can start 17 in the note packet while I do some erasing. Okay. Okay, so for the first one, we're showing that tautology. What's the first step? Put your P's and your Q's and put all the possible truth values. True, true, false, false, true, false, true, and now, truth table next. What is the procedure here? Well, you have a couple of different options, but I would say the easiest thing to do is to break it apart into pieces. We know how implication works. There's an implication, but there's a nested component first, right here. Values of this, and then knowing the truth values of this, we can determine the truth values of the implication. Does that make some sense? Okay, so from here we'll go, all right, P or Q is true when?
When none of these two are false.
When at least one is true, right? Okay, so true, 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 false, true, false, true, true, false, false, false. Okay, and then P implies P or trying to deal with right here. All we have to do is use our rules from implication. You might be saying to yourself, oh no, I've already forgotten what they are. Just think about, if it is snowing, then it is that statement. It would be false if it was snowing, but it was not cold, right? So when the second one is false and the first one is true. So when the second one is false, is the first one true? No state end up false. You can just immediately go, hey, they're all going to be true. Does that make some sense? That is, implications are easy to deal with because you automatically know it's going to where the second thing is false, but the first thing is true. So we look when it's false, and we say the first thing, look, it's not true, so we're good everywhere. Always true. All right, sweet. Hey, last column's all T's. It's a tautology. Great. Now let's show that P implies Q implies not P is also a tautology. Oh, wait, what is this saying? It's saying that the implication P implies Q is logically equivalent to the contrapositive of the implication P implies Q. Yeah? So they say the same thing. That's what we noticed earlier. So let's just run through it. We got P, we got Q. We're going to have quite a number of them here, actually. So let me make sure I give us lots of P, Q, not implies Q, not Q. Oh, I need to write a little bit smaller to make sure this all fits. PQ, not Q, P implies Q, not P, and then finally, P implies Q. I will write this almost vertically, if and only if, okay, let me make it bigger, is Q, not Q implies not P. The final statement that we hope to get all true values for if we've done everything correctly. So lots and lots of columns, a bit more in depth than you need to. I don't think that most people need the not P and the not Q column, but just to be careful, let's put them there. So P, you'll have true, true, false, false. Q, you'll have true, false, true, and false. Not and true. Not Q, we'll do the opposite of Q. So false and true, false and true. P implies Q is false.
P is false.
True. Q is false. Get Q. When is Q false? And P is true. Right here. So that will be our false situation. The other case where P is false, or where Q is false, also has P false, so we're good there. Yeah? Now let's do not Q implies not P. So when is this false? When the second thing, not P, is false, but the first thing, not Q, is true. So let's look at the second thing, not P. When is it false in these first, what are the values of not Q? Not Q is false here, yeah? Okay, so that's fine. But here, I've got not P is true. So this would be false, yeah? Everywhere else, we don't even have to worry. We get trues because not P is true. Yeah? Okay. We do. When is that true? Not always, but yeah, oh, here always. Yes, absolutely, it's always true here. Yeah, they're true when they both are true. So same truth value, it's true. Same truth value, true. Same truth value, true. Hey, it's a tautology. So that's a true statement no matter what happens with P and Q. That is, P implies Q is logically equivalent to not Q implies. I want to have some sort of a sense that if they put this arrow in between two things, it automatically makes them logically equivalent. Statement involving false, That is, it could be the case that you don't end up with a column of all truths. Maybe one of the things ends up being false. In that case, it would be a false statement that the two things are logically equivalent, right? Anytime you get a tautology, then they are indeed logically. Okay. Okay, to wrap it up for today, after all, it's Friday of the first week, and we've already finished section 1.2. We're running a little tiny bit ahead. This is great. Awesome. I will not see you on Monday. I will see you the Wednesday of next week. You can all celebrate Labor Day. Cool. See you around. Have a great day.